My God. Hello, everyone. You have no idea how powerful this section is. We're going to be solving square system using Kramer's rule, which is roughly speaking by using determinant computations. And this will be very useful, especially for applied problems where the numbers are not going to be nice, clean integers. So this is going to be really a lifesaver for a lot of those systems that are more applied. And if I had to categorize 3.6 and 3.7, solving a 2 by 2 system, do it with the inverse. Solving a 3 by 3 system, do it with Kramer's rule. That's typically a good strategy that is very efficient for most questions that you're going to face. So let's solve some square system using Kramer's rule. So again, here I'm just going to show you the method. So the second way to solve a square system. And really here, as a remark, this is really for 3 by 3. I am going to do it for 2 by 2, but me, if I had a 2 by 2, I would do it using the inverse. So how do you use determinants to compute the unique solution of a square system? So again, here, this trick only works if the the coefficient matrix A is invertible. In other words, the determinant cannot be 0. So suppose you have a square system, even if I'm showing you the general method, because this works for n by n square system, we're just going to be doing it mostly for 3 by 3s. Sometimes if you want, you can do it for 2 by 2s. So how do you get the unique solution? So we know when A is invertible, there's only one solution. So here, the way you're going to get your solution constructed, the first thing you do is you compute the determinant of A. We know that number is not going to be 0. And then the first variable of your system, x1, is going to be the ratio of the determinant of A1 over the determinant of A. But what is A1? So A1, or here I wrote AJ, but A1 in particular, A1 is the matrix where you replace the first column with the B vector. So you get rid of the original vector, the original column 1 of A, and you replace it by B. So when the first column is replaced by B, that's A1. And you compute that brand new determinant for that brand new matrix. You take the ratio, and that's the value of your first variable. And then if you want x2, what do you do? Well, you compute the determinant of A2. What is the determinant of A2? Well, you replace, so A2 is a matrix where you replace the second column. So that sentence here works for every single AJ from j equal 1 to n. So you replace the second column by B. You look at this brand new matrix, you compute the determinant, and the ratio of those two numbers will be the value for x2. And you do this for all variables. So the last variable, the value of the last variable in your unique solution is going to be det an over det A, where an is the matrix A, where you replace the last column, the nth one, by B. And this gives you your unique solution. Typically for you, it's just x1, x2, all the way up to x3. But this works for any n by n system if you know how to compute determinants for n by n matrices in general. Just a small remark too about Kramer's rule. One of the power of this method is that if you are looking for only one value of your unique solution, so if you have x, y, z, and you just want y, then you can compute det 2 over det A, and you can get that value for that one only. So that's also one advantage of using Kramer's rule. If you only need one value of your unique answer, that's a very nice way to use, or a very nice argument to use that method. Anyways, the best way to really assimilate this is by looking at some example. So I have a 2 by 2, then a 3 by 3, and then of course you're going to have fun playing with that stuff. So let's solve this square system, and I'm forcing you to use Kramer's rule. This is not something I like to do. Like normally when I ask you to solve a system, I don't care. You want to do it Gauss Jordan, you want to use the inverse or Kramer's rule, do whatever you want to do. That's kind of a personal question, but I'm expecting you to be masters at solving square system. Okay, no square system should give you any fear, because you know at some point you will know Gauss Jordan, you will know how to compute inverses, you will know how to use Cramer's rule. One of those tricks will be your favorite one that you use well. So you're going to be very good. Anyway, so here's my 2 by 2 system, and the matrix A is given by 5, minus 3, 6, 11. So that's my nice matrix A, my column of variable xy, and then my B, my augmented vector, 7 minus 4. So that's my system in matrix form. So the first thing I do, okay, is to compute the determinant of A, just making sure there's a unique solution here. So I draw my little fishy. Okay, so AB go. So I rewrote that. See here, let's do it again here. So if you do 5 times 11 minus 3 times 6, verify that's 73, and that 73 is not 0. So we know A is invertible. We know there's a unique solution, but now I'm going to do it using using Cramer's rule. So here the idea is that my column 7 minus 4 for the x, so I like to use ax instead of a1 for the x variable. It's up to you, different notation, still good. So here the first column, so here my first column of A is replaced by B. So here the only thing you have to do first is replacing the first column of A by B, and this will be your AX or your A1. So here only the first column, okay, is replaced by B, and now it's time to compute a brand new determinant. So there's a new fish. That's the power of this. So especially for 2 by 2, normally you guys are good at drawing fish. So you draw your fish. So 7 times 11 minus 3 times minus 4. Verify that this is 65. And actually, as soon as you have 1, or if I'm only asking you for x, you can write the answer for x. X will be 65 divided by 73. That's your answer for your unique solution. That's your x value of your unique solution. And then again, so for AY, you replace the second column by B. So again, here, make sure you feel it. I'm just replacing the second column, so A2 or AY by B. So that's my B. I just want to make clear, like, replacing those column by B here. And then it's time to fish. Okay, so time to fish. So if you draw your fish, 5 times minus 4 minus 7 times 6, verify that this gives you minus 62. And this is your value. And then your value for y is minus 62 divided by 73. And that's your unique solution. Again, I must make that remark clear. If I was just looking for x, the x value of that unique solution, you could have simply computed det ax and your det a and compute that ratio, and then just give me that one number. But if you want both pair of numbers in your unique solution, then you have to also do it for ay. All right, that's it for that 2 by 2. So again, here, just be organized, be good at computing determinants. This is going to be really solving a lot of issues. So 3 by 3, this is where this method really shines in general. Solve the following square system using Cramer's rule. Again, make sure you know how to write your system in matrix form. So the coefficient matrix, 1, minus 3, 2, 4, 5, minus 3, minus 2, minus 6, and 1. The x vector is x, y, z, just the variables together, and the b vector, 5, 2, and 0, that I just bring together. And now it's time to compute some determinant. So here I'm just writing the answers. Computing 3 by 3 determinant is fairly long, so you have here a lot of good examples. So make sure you double check, triple check my computations. I might have done mistakes here, but if you are, as an exercise, computing the determinant of A, please verify that the determinant of A is minus 47. Now I'm going to replace the first column to compute AX, to construct AX. So I'm replacing the first column by 5 to 0. Make sure that you try to compute the determinant of this brand new matrix where the first column is replaced by B. So if you do it, please double check that this is going to give you a nice minus 83. And then you construct a y where you take a now and you're just replacing the second column, the x column, by b. So here I'm replacing the second column by b. Make sure you try. This is like nice. These are nice for practice example. Make sure you compute your determinant using your formula or any way you understand how to compute this 3 by 3 determinant. Double check that you get 20. And then finally for z, you first construct the matrix AZ by replacing the third column, the Z column, by the augmented part. Again, compute the determinant, verify, please do it, good practice. 4 determinants right there. You cannot say that I do not have enough practice. Shut up. You have 4 right there. Kramer's rule forever. When you do that determinant, please double check that this gives you minus 46. And now for the final answer, so what is the value of x? Well, it's det ax, which is minus 83 divided by minus 47, which simplifies to 83 over 47. Y is 20 over minus 47, which I like to put the minus on top. So you get minus 20 over 47, and z is minus 46 over minus 47, which simplifies to 46 over 47. And here, even if you're good at Gauss-Jordan, finding that answer using Gauss-Jordan, that fraction answer, good luck. You're going to have like a hard time getting this number, this solution using Gauss-Jordan. I think Kramer's rule is just so clean. Like these determinants, especially if your coefficients are nice integers, and even for the more trickier questions, it's just computing determinants with 3 by 3 are basically a bunch of multiplication. It's easy to make a mistake, especially when you're stressed. I am fully aware of that, but this course is more about the method than anything else. So getting to the answer using Kramer's rule is, to me, for 3 by 3 system, especially for some of these applications that we're going to see in the next chapter, this is pure gold. All right, enough of my joy here. I'm going to go relax now. So this is the end of that section. This is also the end of that chapter. So remember, solving square system, 3 by 3 system, number one way would be, to me at least, to use Kramer's rule. But do whatever you want. So anyways, I'll shut up. I'll shut up now. Yes, now? Should I? Yes. Anyways, all right, for that section and this chapter, that's it. That's all. Bye-bye.